Pi there, the parabola, level 1. Just some easy examples by the pi. Let's begin. Let us first define what a parabola is. By definition, a parabola is the set of all points in the plane that are equidistant from a fixed line, which we usually denote by D since it is called the directrix, and a fixed point which we usually denote by F since it is called the focus. And the key condition here is that this fixed point must be not on the fixed line. So to understand what this means, let's have an illustration. So say we have this fixed line which is D and a fixed point F. How would the parabola look like? It would look something like this. So you can check clearly this one has the same distance as this one. If you get this one, the distance from the point on the parabola to the directrix refers to the perpendicular distance since that is the shortest distance. So this thing would have the same distance as this one. So is this one there. That is the basic thing to remember in parabola. So once you have that one, let us define more terms. So we still have our illustration out here, and let us first define the line passing through the focus perpendicular to the directrix is called the axis of symmetry. How would that look in our illustration? It would look something like this. So this is the axis of symmetry, a line that passes through the focus and is perpendicular to the directrix. Next thing to note, the point of intersection of the axis of symmetry with the parabola is what we call the vertex. So point of intersection of this red line with the parabola would be out here, the vertex. Just disregard the 0, 0 out here. That would play a role later on, but the thing to note here is that we usually denote the vertex to be V. And in some other definition, we usually define the vertex as the max point or the minimum point in a parabola. Since as you can see, if this parabola extends out here, then this one out here is like the top of that parabola. Last thing to note, the line segment through the focus with endpoints on the parabola and parallel to the directrix is called the latus rectum. So how would this look like? Like this. So as you can see, this is a line that passes through the focus and it has endpoints on the parabola parallel to the directrix. So why did we define these three more terms? Well, they would play a role later on in how we construct and sketch precisely the parabola. Now that the definitions are out of the way, you might be wondering, equations please? And this would be the equation for the parabola. Just take note that I would run through this since this is just for formality. I don't really use these formulas that much except for this equation and the orientation. So let's go over this. So for the equation of the parabola, we have two forms. One is given by quantity x minus h squared equal to 4p times y minus k, and quantity y minus k squared equal to 4p times x minus h. This p here would play a role later on. That's why we need to factor it in this way. Also take note that here the squared variable is x, so you kind of expect that this is a equation for a parabola that has something like this or this, since this would have two x values in just one y value, and this thing would also have two x's value for just one y value. The same idea applies for this. One more thing to take note here is that this one represents the vertex, so take note of that. And then for the focus or in directrix, I'll just go over this one. So for the focus, we have basically from the vertex, you change the y coordinate, and then for the other one, you change the x coordinate. So as you can see, the p here plays a role. For the directrix, so this one is, instead of adding p, this time we subtract p on the y, this time line, and the same idea applies out here. But this next one is important. For the orientation, again, this one we expect it to be oriented vertically. So the p here determines whether it opens upward or down. If it is positive, it opens upward. That means it would look something like this. If it opens downward, p less than 0, it looks something like this. Next, for the second case, we expect it to be oriented horizontally. So if p is greater than 0 or it is positive, it opens to the right. It looks something like this. And if it is less than 0, it would look something like open to the left. Please remember this orientation things since it would be really important later on. One more thing to note here is that the length of the latus rectum earlier, again, this is the line segment passing through the focus with endpoints in the parabola. It has a length of absolute value of 4. So take note of that one. This would be important, this would be important, and this would be important. If you're wondering how to prove this one, I will put a link in the description down below. In particular, I worked on the proof of this one in a previous video at the point 0, 0 out here. The one that I would put in the link down below, that would be nice if you check it out. So now that these are out of the way, let's go on with some examples. points. First example, our goal is to find the vertex, focus, equation of directrix, and the endpoints of the latus rectum of the parabola given by x squared plus 8y equal to 0 and provide a sketch of it. So as you can see, I already put the things that we need here and a xy plane. So first step is to convert this equation to the one that we know. So take note that x squared plus 8y can be written of this form. Basically, you just move 8y to the other side, do some factoring, and write x in terms of this. So that's pretty straightforward. And from here, we can easily obtain the vertex. The vertex here represents the point, this one, and this one. So we'll have the point 0, 0. It would be located here. Now for the orientation, since here the variable with a square is x, this means you kind of expect that the parabola must be oriented vertically. And the one that would determine whether it is oriented upward or downward is -2 out here. So again, since this one is negative, from earlier you have to expect that the parabola would be opening downward. So it is oriented vertically and opening downward. So it would look something like this one. So next, we find the focus. So for the focus, based on the illustration, you'd expect that it would be something around here, since the focus must be inside the parabola. And then to do that, we know that it must be in line with the vertex. So we won't be really changing the x coordinate out here. We'll just be changing the y coordinate. And the determiner of what would change that y coordinate is the p as well out here. So what you'll do here is you'll add -2 or subtract 2 if you want to obtain this. So the focus would be the point 0, -2. So as you can see, you don't really need to remember the formula. All you need to do is to remember that this p plays a huge role in constructing the sketch and the parabola in general. For the directrix, you know that this one must be equidistant to this one, which would be the directrix. So you know that it must be a horizontal line since it is a parabola that is oriented vertically. And since we have a horizontal line, you expect that this one must be of the form y equal to something. So what will determine that value is, again, change this one, but this time add 2 to move it up. So it would be something like this. So we have your y equal to 2. And then lastly, for the endpoints of the latus rectum, we know that the latus rectum would be something around here with endpoints out here. So the key to determining the latus rectum is just remember that its length is given by the absolute value of 4p. If this is p, 4p is given by 4 times -2, absolute value, that would be 8. So if this one is length 8, you expect that this one must be length 4 and this one must be length 4, which means that the endpoints of the latus rectum would be -4, -2, and 4, -2, since basically we subtracted 4 and added 4 on the 0 or the x coordinate of the focus. And that finishes this problem. We were able to obtain what we want and give a sketch of it. Let's now move on to our second and last example. Similarly, what we do is we find the vertex, focus, equation of directrix, and the endpoints of the latus rectum of the parabola, this time given by y squared minus 4y plus 2x equal to 0, and provide a sketch of it. So for the first step out here, again, we convert this to our known form. So we have here, so take note that y squared minus 4y plus 2x equal to 0 can be written of this form. How was this obtained? Basically, you move 2x here to the right side, and then you use completing the square on this one. I won't dive into the calculation process of that one since our focus in this one is sketching the parabola, so I'll leave that one to you. So once you have this, we can now obtain the vertex. Vertex is just this one, so we'll be having the point 2, 2, and it would be plotted out here. Next, for the orientation, again this time, since the squared variable is y, you kind of expect that if we have 2 y's out here, the parabola would be oriented like this or like this. To determine if it opens to the right or opens to the left, that would be dependent on the sign of p. In this case, since it is negative, then we expect that the parabola opens to the left. And since this one is the vertex, the parabola would do something like this one out here. So for the focus, since this one is the parabola, you expect that the focus would be around here, inside the parabola. So given the vertex, what you'll change is the x coordinate, and that would be dependent again on the p. So that means the focus would be the point 3/2 and 2. Since what we did is, given the vertex, we just subtracted 1/2 out here, since we know that it must move to the left. On the other hand, for the directrix, you expect that this one must move to the right. So given the vertex, its x coordinate, focusing on that one, instead of subtracting 1/2, this time we add 1/2 to obtain 5/2, and we know that the line must be vertical. So if vertical line, that would be x equal to something. So that would be x equal to 5/2. So we now have the directrix and the focus. For the latus rectum, same strategy as earlier. We have this P, we compute for 4P. Computing for that one, that would be 2. So you expect that from the focus, this must be length 1 and this must be length 1. Since the focus is given by this and we are changing the y coordinates, we just add 1 and subtract 1 to 2 on the y coordinate to obtain the points 3/2, 3 and 3/2. This is the answer for this problem. We are able to obtain the necessary stuff that we want and give a nice sketch of it. Just some final word out here. If you haven't checked it, please help me provide better math content to you by answering the Google form in the description down below. It's just 3 questions that asks you what you liked about the video, what you disliked about it, and tips for me to help you in your journey in math. So if that is too hassle for you, you can just check the comment section down below and type what you think can be improved in these videos, and I'll be glad to read those. So yeah, I hope you learned from this one, and that's it. Have a nice day.